Welcome back to today's session. In the previous sessions, we had seen two special cases of LPP. One was assignment problem, other one was traveling salesperson problem. As such, traveling salesperson problem was a restricted case of assignment problem. Today we will be looking into a new problem which is also a special case of LPP, and this problem is called transportation problem, right? This problem is called transportation problem. What is this transportation problem all about? So here we will have a look at what is transportation problem. Transportation problem is one of the special cases of LPP in which the objective or the goal of the problem is to transport various quantities of a single homogeneous commodity that are initially stored at various origins to different destinations in such a way that the transportation cost is minimum. See, when I read out this, a portion of it you people might have understood, but actually, what is the problem all about? If at all I need to explain it in simple words, let me assume there are some three or four factories that you have. All the four factories are producing the same commodity, same item, right? And you have five shops of yours. The sales does not happen in the factory, and production does not happen in the shop. So from the from the factory to the shop, these items or these goods have to be transported, right? So when these goods are being transported, how will they get transported? See, every factory has a certain capacity of production. You might ask me, sir, why four factories? We could have a single factory and all that we wanted to produce, we can produce in one place only. No, the factory has a certain limitation called capacity. If at all a factory can produce, let me say, 10,000 items, then it can produce only 10,000 items. If at all my demand is more than 10,000, I need another factory, right? So for that reason, I have four factories and my sales happen at the shop, and these goods, these commodities which have been manufactured in the factories have to be transported to the shops. So can I transport it anyway? See, if at all I don't take uh, ample care of this transportation, then many a times the situation will be like the cost of the commodity will drastically increase. Many a times it might so happen that the cost of production is less than the cost of transportation. So this problem basically talks about identifying or looking into this transportation of goods from the source factories to the destination shops. Fine. And we are supposed to find the routes in such a way that the overall transportation cost, the cost of transporting the commodities from the factory to the shops, will be minimum. Hope now you have understood the objective of the problem. So to achieve this objective, we must know the amount and the location of available supplies. That is, when I say amount, it is the capacity of the factories, and location specifies the distance that has to be traveled, and the quantities demanded. See, I cannot sell all the commodities in a single shop. Right? In a particular area, the demand for the commodity might be very high. In another area, the demand for the commodity might be low. So every shop will have a certain demand factor. So you will be transporting the goods based on the demand of the shop. Right? Like you have capacity for the factory, you also have demand for the shops. Like you have capacity for the supply, you have demand for the receipt of commodities. Okay, the cost that results from transporting one unit of the commodity should be known. Right, if at all I am moving one unit of the item from source I to source J, then what is the cost incurred for this should be known to us. Fine? Fine? Hope you've understood. So the cost that results from transporting one unit of commodity from various origins to various destinations also should be known. So from each source to each duration, if at all I am transporting one unit of the commodity, how much cost will be incurred? This should be known to us. Only then we will be able to find out the least cost transportation between the source and the destinations. So what all should be known? The number of sources, the number of destinations, capacity at the source, demand at the destination, and the cost of transporting from each source to each destination. This much information should be known to us. Only then we will be able to solve. Hope by now you have understood what is transportation problem. So after understanding what is transportation problem, we will see how a transportation problem looks like. Right? The structure of a transportation problem. So the transportation problem seeks to minimize the total transportation cost of transporting goods from M sources. I have M sources. Source S1, source S2, source S3, so on up to source SM. M different sources or origins I have. Similarly, I have N destinations, D1, destination D2, destination D3, so on up to destination Dn. I have M different sources and N different destinations. When one unit of uh, commodity is transported from I to J, let me say from source 1 to destination 1, if at all I am transporting, then the cost of transporting one unit is C11. That is what has been specified here. When the unit transportation cost from source I to the destination J is Cij. Okay. So maybe from these sentences you might not have understood much, but look at this diagram, you will be able to understand quite a lot. See, I have M different sources and N different destinations. For transporting from source 1 to destination 1, the cost is C11. From source 1 to destination 2, cost is C12. Source 1 to destination 3, cost is C13. So on. source 1 to destination n, the cost is C1n. Okay. Similarly, you will have individual costs for transporting from source 2. Similarly, from source M. Okay. So for every ith source to the jth column, if at all I am transporting 1 unit of the commodity, then the cost incurred is generally denoted by Cij. I represents the source and J represents the destination. Okay. For every source, I have an associated value called capacity or supply. S1 is able to supply A1 units. S2 is able to supply A2 units. SM is able to supply AM units. Okay. These are the capacities. Similarly, the requirements or the demands of the destinations are also given. For every destination, you have an associated value BI, right? So for destination 1, the demand is B1. For destination 2, the demand is B2. For the destination 3, the demand is B3. Similarly, for the destination N, the demand is Bn. Okay. So you know that there are M sources, there are N destinations. For every source, there is a capacity, and for every destination, there is something called a demand. And we also know the cost matrix, which represents the cost of moving 1 unit of the commodity from ith road to ith source to jth destination. This much is known. But in the figure, there is one more factor, Xij, which we never spoke about. What is this Xij? See, this cost represents the cost of moving 1 unit. But how many units you are transporting, right? How many units you are transporting, that decides the total cost. Okay. So your Xij is the quantity of the goods you are transporting. So let me say from S1 to D1, I am transporting 10 units. Then X11 will be 10. Let me say I am not transporting goods between S1 and D2. Then what should I write X12 as? Very simple, I'll write 0. Right? If at all I am transporting a certain quantity, I'll write the quantity here. If at all I am not transporting, I'll write a 0. Is there a possibility to transport negative values? Impossible, right? So Xij is your decision variable. It is a non-negative variable. You can transport 0 or more number of quantity from a source I to the destination J, but you cannot transfer or transport negative quantities. Hope you have understood the structure of the transportation problem. Quite good. Shall we move on further? So now we talk about LPP formulation or linear programming formulation of your transportation problem. So what is the basic structure of linear programming? If at all you need to call a problem as linear programming problem, it should have an objective function which has to be either minimized or maximized, and it should have a set of constraints, and it should have a non-negativity constraint. Let us see, do we find all that in a transportation problem? So the linear programming formulation in terms of the amounts transported from the source to the destinations Xij can be written as, see, how do you decide the cost? It will be cost per unit into number of units that you are transporting. Fine. So that is what has been written here as our objective. The overall cost has to be minimized. So I am writing min. The objective function is normally denoted by z. So z equals double summation of Cij Xij. Cij is the cost per unit and Xij is the number of units. So cost per unit into number of units transported will give you the total transportation cost. Okay? Any doubt with this? So the objective is clear. So the objective is minimize z equals double summation Cij Xij. Okay? Then what are the constraints? See, your total quantity that you transport from a source cannot exceed its capacity. If the capacity of a factory is 10,000 and you are showing that you are transporting 12,000 units from there, where did the remaining 2,000 units come from? So that will be a question mark, right? So how much ever you are transporting, that should be equal to the capacity of the source. So that is the constraint. So that is what has been written here. The constraint is summation Xij is equal to Si. For each source, the quantity of transportation from the source should be equal to the capacity at the source. Okay. Similarly, you have a constraint for the destination as well. If at all my demand was only for 3,000 items, you come and dump 10,000 items on me. What will I do with the remaining items? It is a dead investment, right? It will not make profit. So I should transport only the number of items demanded by a destination. So when I take the summation of Xij for every destination, then it should be equal to the demand of the destination. Okay? So this also is understood. Then the non-negativity constraint. This I already explained. See, Xij is the quantity of transportation. You can transport either zero number of items or more than zero number of items. Negative quantity of items cannot be transported. Therefore, Xij should be greater than equal to 0. So the LPP formulation is fine now. So the LPP formulation or the mathematical formulation of transportation problem is minimize Z equals double summation Cij Xij subject to summation Xij is equal to Si and summation Xij is equal to Dj and Xij is greater than equal to 0. Hope the concept is simple. Hope you people have understood. Quite nice. So shall we move on to the next slide? So we need few basic definitions here. We will be using few terms. So first term is feasible solution. What is feasible solution? Any set of non-negative allocations which satisfies the row and column sum is called feasible solution. See, if at all you are transporting certain number of quantities in such a way that the source capacity and the destination demand both are getting satisfied, then such a solution is called feasible solution. Fine. Then the next term is basic feasible solution. We also call it BFS. Right? A feasible solution is called basic feasible solution if the number of non-negative allocations is equal to m plus n minus 1, where m is the number of rows and n is the number of columns in the transportation table. So for you to understand, I'll move back to the previous slide to show you the diagram. See, when I say the number of allocations, the number of allocations is nothing but the quantities that I have specified here. I might be transporting from S1 D1, then I might be transporting at S2 D2, so two allocations are done. I might not be transporting at X1 X13, and I might be transporting through X23. So the number of allocations is 1, 2, then 3. I might be transporting from XM3. So that will be the fourth allocation. Then I might be transporting certain quantity at XMN. So that will be the fifth allocation. So the allocation means Xij values being greater than 0. A non-negative value of Xij is called an allocation here. In this transportation problem, whenever I write the Xij value to be greater than 0, that is considered as an allocation. If the number of allocations that I have made is equal to number of rows plus number of columns minus 1, then it is called a BFS. Okay, in BFS you have two types. One is non-degenerate BFS, other one is degenerate BFS. What is non-degenerate BFS? Any BFS of a transportation problem with m rows and n columns is said to be non-degenerate if it contains m plus n minus 1 allocations in independent positions. What is meant by independent positions, you will be able to understand in the later sessions, right? As of now, for you to understand the definition, non-degenerate BFS is a BFS where m plus n minus 1 allocations are in independent positions. Okay. Then what is degenerate BFS? If at all the number of allocations that I have got is less than m plus n minus 1, right? If it is less than number of rows plus number of columns minus 1, then such a feasible solution is called degenerate BFS. Okay, hope the definitions are clear. Then how do we go about solving a transportation problem? See, the solution process of a transportation problem is done in two phases. The transportation problem is solved in two phases. In the first phase, we obtain initial basic feasible solution. We call it IBFS. In phase 2, this IBFS will be considered as the problem and we try to optimize the solution. For a given problem, in the first phase, I find IBFS. In the second phase, considering the IBFS, I will try to optimize the solution. Okay. In phase 1, the minimum cost procedure can be used to establish the initial basic feasible solution, which is IBFS, without doing numerous iterations. With a single iteration, you can arrive at the IBFS. In phase 2, by using either Modi method or stepping stone method, we try to optimize this IBFS and find an optimal solution for the transportation problem. Okay. So for computing IBFS, we have three methods. They are northwest corner rule, least cost method, and Vogel's approximation method. Similarly, for optimization, we have already shown here, you have two methods. One is Modi method, other one is stepping stone method. Okay, so these methods we will be looking into in the next session. Shall we wind up here? Hope you people have understood the concept of transportation problem. Thank you. Be home, be safe, have a nice time, enjoy.